Hi folks, in this video we're going to talk about block diagrams. Block diagrams are going to be useful in our modeling section as they're going to be a graphic representation of a system. So we're going to take our equations and we're going to make a picture with them. And this is going to allow us to visualize the flow of signals between different elements in the system. So when we talked in our administration and our introduction section about the control loop, we drew in a block for the plant. Remember, the plant is our system, and we drew in a block for a sensor, and we drew in a block for an actuator and a controller. And so between the blocks we had these little arrows, and those denoted a signal going from one block to the next. So we're going to look at how those signals move, and we're going to look at how the blocks are designed and how we can combine them together. What this does for us is it allows us to take equations and put it into something that's going to be a little easier for you to see, a little easier for you to think about. They do say a picture's worth 1,000 words. Well, a picture's worth a lot of equations too. And then the second step of it is once we've got all these equations into picture form, we'll do algebra on the picture instead of the equations, and that's the reduction part. And reduction just means we're going to take two blocks and we're going to combine them into one block. And if we keep repeating that process, we're going to end up with, instead of a whole loop with a bunch of different blocks, or maybe multiple loops, like the example that I'll show you in the next video, we're going to end up with just one block that corresponds to one input and one output. And that will describe the entire system. Even though we may start with a whole bunch of equations, we'll end up with one complicated equation, and we can do it using pictures, which will be lots easier than doing the equations. When you try to do the algebra by yourself, sometimes it gets difficult figuring out, well, which part do I want to isolate, which part do I want to substitute here or there or the other place. And when you do it in a picture, it gets to be a little easier just because of the tricks we're going to show you. So let's start with the block. The block is the base here. This is the important part. We call it a functional block, and sometimes we just call it a block. I'm just going to call it a block. And so inside the block goes a chunk of our system, or the entire system. But we're going to be able to take our system, and this will make a little more sense when we talk about different types of systems and we do some modeling. But we're going to take our system and we're going to take pieces of it, split them up, and put them into individual blocks. Now, you'll notice that this is denoted as G of S. That's because we're going to use a whole lot of transfer functions, and transfer functions are going to be functions of S. S is the Laplace variable. Now, our block also has one arrow going in and one arrow coming out. Those are our signals. The function goes in the middle, input goes into one side, output comes out of the other side. You could reverse this, and the input could go into the right and the output could come out of the left. It doesn't matter which way you do it. But what it means is the output is the function, the thing inside the block, operating on the input. Now, that function could be all sorts of different things, but like I said, in our case, we're going to use transfer functions. Transfer functions are going to be a wonderful, nice thing because they're going to be linear, and they're going to relate a single input to a single output, which is exactly what we've got here in the block. Now, because it's a linear system, and again, we're going to talk about linearity, or if you're watching this video late, we already talked about linearity, so remember linearity. Because it's a linear system, we can say that the output then is G of S, the function, multiplied by the input. That's the beauty of linearity. And so if we've got just the function multiplied by the input, you can see that if we stack these up, we can start just multiplying them across, and that's block diagram reduction, which we're going to get to. So remember, inputs and outputs are signals. Signals. The block is a system. We're going to have trouble sometimes in Laplace differentiating between systems and signals because they're all going to look the same in equations. But in a block diagram, they look very different. Also, think about your op-amps. Just like we did in Lab 1, when we built an inverting or a non-inverting amplifier, we had a signal, V sub in, and we had an output signal, V sub out. But nowhere in there did we draw the power. The power doesn't show up in here. If there's an energy source, it's not included on the block diagram. All we include are the signals in and the signals out. So here's a couple of examples of types of blocks. And this is just ideas to get you started in how you chunk up your system. If we have a point mass, then we could say that the force goes in and the acceleration comes out. And so if you think about F equals m times a, in this case, a equals F times 1 over m. And so the point mass block system as an equation could be represented as 1 over m. But we could also say force goes in and velocity comes out. Well, velocity coming out, that's going to be an integral, which in Laplace is really easy. Or position comes out. Again, it's a double integral, and in Laplace that's really easy. So that's going to end up still just as a function of s. If you don't know what function of s I'm thinking of, review your Laplace notes. Another example is that your car steering system. If you turn the steering wheel by a set angle, then you expect the heading of your vehicle to change. Now, how does it change? Is it a one-to-one relationship? Probably not. Is it going to be an integral relationship? Is it going to be a differential relationship? It could be more complicated than either of those, but still, you know that the input to the system is you turning the wheel, and you know the output of the system is that the car changes direction. Now, you could also go through and you could isolate different blocks representing little functions all the way through there in terms of the different components of the steering system, or you can look at a block holding all of it all together. In this case, you could think of it as modeling components or modeling the whole thing. If you model the components, you could do block diagram reduction and end up with the entire thing. Also, there are some work done in terms of applying block diagram and system representations to biological systems. One that I've seen is about T-cell response to allergens and such. If you've got an immune system, the immune system is a system. It could fit in a block. Now, an immune system is not going to be linear, and it's not going to be easily modeled with a transfer function, but still, it's a system. And if we take some sort of environmental sample, say when you are breathing, you're breathing in bits of the environment, it reacts with things in your sinuses and your nose, and that's going to trigger a response. Well, that triggering, that is the system responding to an input, and the output in this case is some sort of white blood cell response. Now, I'm not a biologist, so I'm not going to tell you too much about that, but I know that there's been some interesting work done in modeling that system. Now, when you model that system, it becomes very complicated. But we're going to focus more on the simpler sorts of things like the point mass and the car steering. Also, as your signals propagate, we need to think about a couple of other things in here. One of them being summing junctions, and another being branch points. If we've got two signals that need to combine, we use a summing junction, which sums them together. In this case, there's a little plus and a little minus. In Simulink, you'll see that it can be either a circle or a rectangle, but either way, it's all the same thing. The plus says that you're adding that signal to the output, and then the minus says you're subtracting. So in this case, A with a plus, B with a minus means plus A minus B, which we drop the plus and it's A minus B. A branch point is if you've got one particular output that needs to go to two other inputs of blocks. Well, you just split it, and so A goes to all three here. So if we take what we've talked about, we can start doing block diagram reduction. And so you can see we've got a cascade or a series connection where you've got two blocks in series. We've got a parallel connection where we add the results. We've got a pick-off point, that's the branching point. We can move it from one side of a block to the other. We can move a summing junction from one side of a block to another. And that last one is really critical, the feedback loop. And this is what you're going to see a lot of in this class. Now, you don't need to memorize this chart. This chart is in your book. Go check your book, you'll find it. But let's look at the series connection and just run through it so you can see how this works. If we've got signal X going into block G, and block G provides output Y, which is then input to block H, which has output Z, then we can look at just G to start with, and we know that Y is equal to G times X. Also assume that G and H are linear. I forgot to mention that. And if we look at block H, then Z is H times Y. So if we combine those together, then obviously Z is H times Y, which is H times quantity, G times X. And since this is all linear, we can combine those together and say it's H times G times X. So then we've got just a single block. X goes in, Z comes out, and the function in the middle is G times H. Which you can see I've switched the order from H times G, and that's because they're linear systems. If this was not a linear system, I couldn't do it. In fact, I'd have to make it much more complicated. But because of the linearity, we can reverse that order, and we frequently do. In a feedback system, R is my reference input, that's what I want it to be. E is the error between the reference input and B. Typically G is the system in this case, and H is a sensor measuring the output, C. So if I look at the blocks individually, then C, the output of G, has to be equal to G times E, and B, the output of H, has to be equal to H times C. So if I look at the summing node then, E, the error, is R minus B, and if I do just some basic algebra, C is equal to G times the quantity R minus B, and we know that B again is H times C. So rearrange it, and C, the output, is G over 1 plus GH times R. So that's a single block. R goes in, C comes out, and the function is G over 1 plus GH. So there we go. We've done a little bit of simple block diagram reduction, and you're going to have to just practice with these before they start feeling real natural. That's right, that's the last slide I've got. I'm going to record a second video here that'll be just as short, and we're going to go through a simple example of block diagram reduction for a real system model, a DC motor. So, watch the next one too.